Welcome to physics online session. In the previous class we have discussed the potential energy of system of charges. In this class we will discuss electrostatics of conductors. So based on the response to electricity, the materials are classified in solids are classified into three types: conductors, semiconductors, and insulators. Okay, so in this present chapter we will discuss about these two briefly. The next last chapter we will discuss semiconductors. Okay, now what about what are the conductors? The present topic is electrostatics of conductors. First we have to know what is a conductor. So examples of conductors are metals. Metals are good conductors, okay, in which the electrons are free charge carriers. These are the responsible for electric field and electricity. These are mobile charge carriers. Okay, so uh, in the absence of any electric field they cannot move. Okay, so but in the presence of electric field they can drift in one direction. Okay, so in this class we will discuss the electrostatics of these conductors. Right, the first property, electrical property: inside a conductor the electrostatic field is zero. Let us consider a conductor, so whether it is charged or uncharged. When it is uncharged conductor, if you take a uncharged conductor, okay, where there is no charge is given to the conductor, so there will be no electric field. Definitely you know it. Okay, no charge, no electric field. So electric field is a source of charge, so if there is no charge, the electric field inside the conductor is zero. Okay, when even though the conductor is charged, so here it is a charged conductor, so I gave a positive charge to this conductor. Okay, so this positive charge is uh, adjusted such that the electric field inside a conductor is zero. Okay, if you take any point here, the net electric field, so the net electric field due to these charges is zero. Okay, so now the third case, so it is uncharged conductor, definitely electric field inside a conductor is zero. Even though it is a charged conductor, so electric field, net electric field inside a conductor is zero. Okay, now I'm taking one more conductor which is in a rectangular shape. You can take any shape of conductor. Let us take one more conductor. Now this conductor is placed in uncharged. This is uncharged conductor in electric field. I have placed this conductor in external electric field. Okay, when you place it in an external electric field, so what happens in this case also, the electric field inside the conductor is zero. In three of the cases, so electric field inside the conductor is zero. So why it is zero in the third case? So I told that when you apply electric field the charges drift in one direction, but why it is zero in this case? Well, why the electric field is zero in this case? When you apply, for example, there is no electric field, so so electric field definitely inside a conductor is zero. But when you apply electric field, what happens? So we to uh, to discuss this topic, we have to know how charges move in the electric field, external electric field. If you place a positive charge in the external electric field, it moves in the direction of, it experiences a force, or it moves in the direction of E bar, electric field, where minus q moves opposite to E. Okay, so here this conductor contains equal number of positive and negative charges. So but electrons are little bit free to move. Why? Because in conductors electrons are loosely attached to the nucleus. Okay, So these charges can move, so and this can move gradually. So if you apply electric field, so one by one charges accumulate on the left side. Why? Because negative, I told that negative charges move opposite to the direction of electric field. So negative charges accumulate here. Okay, so they are moving. So when the equilibrium condition is reached, okay, so total free charges accumulate, total negative charges accumulate on the left side and total positive charge appear on the right side of this conductor. Okay, and the electric field inside the conductor is again zero. Why? Because so here external electric field is E, and internally one more electric field, that is induced electric field, is developed, that is E is external electric field plus induced electric field, one more electric field is developed, E induced, which is in opposite direction and equal in magnitude to the uh, when compared to external electric field. So that net electric field will be zero. In all of the cases, even though it is uncharged or charged, or when it is uncharged it is kept in an external electric field, in all of the three cases, so the electric field inside a conductor is zero. Okay, whatever the situation it is. Okay, this is the first property of a conductor. The second one, at the surface of a conductor, charged conductor, this is a conductor, I took it in a spherical shape, charged conductor, electrostatic field or simply electric field is normal to the surface at every point. So here if you take a point here, so what will be, this is a surface, so this is a surface and this is a normal to the surface. So electric field is always normal to the perpendicular to the surface. This is a surface and it is always perpendicular to surface. Let us assume, let if E were, electric field were not perpendicular to surface, if it is not perpendicular to surface, what happens? Okay, we'll take a negative statement, I'll prove it wrong. Okay, our statement will be correct. So I'll take a let it be the, let say this will be the direction of the electric field. Okay, if it is not, no, it is not perpendicular. Okay, so electric field is normal to the surface. Okay, electric field is normal to the surface. So I am taking, let us assume it is not normal. Okay, electric field is not perpendicular to the surface. No, somewhere it is located. Okay, so then we have two components. We can resolve it into two components. One is a tangential component or component along the surface, and it is perpendicular component, and it is parallel component to the surface. So I divided this electric field into two components when it was not normal. Okay, so when then what happens, then always there exists, always there exists, there exists, okay, a tangential component, tangential component component along the surface, along the surface. So due to this, due to this electric field, due to this electric field, the charges start drift drifting drifting. Okay, but uh, but without any external agency, without, the question is how these charges, this positive charge just move without any external electric field. By themselves they cannot move from one place to another place. Okay, if you give a charge, so they will distribute on the surface of the conductor and come to equilibrium situation. But so what happens when the electric field is not normal? When the electric field is not normal, there exists a one component along the surface. So with that electric field, that electric field pushes these positive charges so on the surface. Because of this movement, so it is reason they can move, they can move until they are responsible for electric field. You are not connecting, so you are not connecting a wire to any battery, still there is a motion of electrons. Is it possible? No, no, not possible. So So the our point is wrong, our statement is wrong. So electric field is not perpendicular, this statement is wrong. Electric field is always perpendicular to the surface of the conductor. Okay, so right. So this is so wrong statement, right? So the second property is electric field is always perpendicular to the surface. Okay, this is about the second one. Next, third one, the interior of a conductor can have no excess charge in the static situation. Okay, let us consider if you take an uncharged conductor, so conductor, what is a conductor? It contains uh, whatever the material, it is equal number of positive and negative charges, but negative charges has loosely attached. Okay, so loosely attached. So okay, so with a small electric field they can move from one place to another place. Okay, but the number is same, so it contains equal number of positive and negative charges. But when a charge is given to it, okay, so when a charge is given to the conductor, how it will be distributed, that is what we are going to discuss. Let us assume in the previous class we have discussed that when the electric field, okay, when according to Gauss law, in the previous chapter Gauss law we have discussed electric field due to spherical shell, electric field inside the spherical shell was zero. Okay, electric field inside a spherical shell is zero. Okay, now I want to apply Gauss law to this conductor. Okay, so here I took Gauss law here. EDS is equals to, according to Gauss law, EDS is equals to Q by epsilon naught, or E into S is equals to Q by epsilon naught. Okay, so here I took a Gauss, for example let us consider a small volume inside the conductor. I took a small volume, sorry, I took a small value. Okay, so this is epsilon naught. Okay, this is a small volume which was enclosed by the surface ds. Okay, so so and now when you apply the Gauss law to this surface, what is the charge? We need to find out, is there any charge in this value? Okay, so according to our statement, there is no extra charge, there is no excess charge in, sorry, the interior of conductor, they have can have no excess charge in the static situation. And I mean when they are in a rest position, so there will you cannot find any single charge inside the conductor. Now I want to apply Gauss law to find whether there is any charge inside the conductor or not. So according to previous topic, what will be the electric field inside a conductor? Zero. Electric field inside a conductor is zero. Okay, what about RHS here? When electric field is zero, so when you will get electric fields, so surface never be equals zero, epsilon naught, it is a constant. So when you will get zero on the LHS, when RHS is zero, then you will get LHS as zero. Okay, so means mathematically we can say that when there is electric field, when electric field is zero, definitely the charge inside the conductor is also zero. When there is a charge, definitely the electric field will be there. So electric field is not there, simply we have to understand that charge inside the conductor is zero, so there is no extra charge inside the conductor. Whatever the charge you give to the conductor, it resides, the charge given to the conductor, resides only on the surface of the conductor. I will write that point here. The charge given to the conductor, to the conductor resides only on its surface, okay, so right, it doesn't go inside the conductor. Okay, so there is no net charge inside the conductor. Next, fourth property, the electrostatic potential is constant throughout the volume of the conductor. and has the same value on its surface. Okay, let it be the a spherical conductor. I took a conductor, it is a charged conductor, so of radius r. Okay, so what is the electric potential here? So from the glass light is clear that electric field on the surface of the surface of the conductor is 1 by 4 pi epsilon naught q by r square. Okay, so it was already discussed in the previous chapter that electric field at any point on the surface of a charged conductor so was derived according to Gauss law as 1 by 4 pi epsilon naught q by r square, where r is the radius of the spherical conductor. Okay, similarly electric potential on the surface will become on s vs nothing but electric potential on the surface will be 1 by 4 pi epsilon naught q by r. Okay, so what is the potential, electric potential on the surface? What is electrical potential on the surface? What is the meaning of this expression? So work done, the meaning of this one, the work done in bringing q from infinity and to arrange or distribute on the surface of sphere of radius r is given r. Okay, whatever the work done in bringing charge and distribute on the surface of a conductor of radius r will gives us the electrical potential at that surface, at any point on the surface. Okay, now what is asked here, what is the fourth property? I want to know what is electric field here, or at the center, here. According to this point, wherever the point you take, whether you take it on the surface or if you take it at the center, if you take the point at the center or somewhere, so electric potential at every point on the volume of the conductor is same. Okay, so at every point electric potential is equals to the value that is on the surface. What is electrical potential on the surface? 1 by 4 pi epsilon naught q by r. The electrical potential inside the conductor also, the electrical potential it has the same value 1 by 4 pi epsilon naught q by r. Why? Because what is electric field inside the conductor? Electric field inside the conductor is 0. So here work done to bring a charge from infinity to infinity and to place at any point on the surface will be this one, that will be electrical potential. So to bring a charge from surface to inner inside of the conductor, you don't have to do any work, because so electric field inside a conductor is 0. Okay, so we don't do any work against the electric field. Okay, so there will be no electric potential. So therefore electrical potential inside and out on the surface of the conductor is equals to 1 by 4 pi epsilon q by r. What is the electrical potential at this point? 1 by 4 pi epsilon naught q by r. Here also 1 by 4 pi epsilon naught q by capital R. At the center also 1 by 4 pi epsilon naught q by r. So electrical potential is constant throughout the volume of the conductor and it has the same value on its surface. Okay, so and the fifth property, the electric field at the surface of the charged conductor is sigma by epsilon naught. Okay, let us take any conductor of any arbitrary shape. This is a charged conductor, so charge is given to it. Okay, so it is a charged conductor. Let us take a surface. So I'm taking a Gaussian surface. It is like a pill box. Okay, pill box, like a tiffin box. Okay, so here charge is on the surface. So here tiffin box, half of the portion is inside of the conductor and half is outside the conductors. Now I want to, and this plus is on the surface, this portion is on the surface of the conductor. Now this is a Gaussian surface. Now I want to find electric field due to this Gaussian surface. How many surfaces are there? This is the first surface, this is the second surface, this is the third surface. Okay, there are three surfaces. Now apply Gauss law. So according to Gauss law, electric flux through the closed surface pi is equals to we have three surfaces, pi 1 plus pi 2 plus pi 3. Okay, pi 3 here, this is a surface direction, but electric field is normal. So the electric field, so when there is a 90 degrees, this pi 3 become what? Pi 3 is equals to EDS cos 90. So cos 90 is 0. So if the electric field and surface vector are perpendicular to each other, then there is no electric field due to that surface. Okay, so yeah, right now, right now I'll take this component, this pi 1. So pi 1 is equals to what? E into, let it be first surface, E into this one is over, now this one, let it be area A, and this is also area A, both are having area A. Okay, so E into A plus pi 2 also having the same area, E into A, but pi 3 is 0. Why? Because the angle between the area vector, this is a area vector, this is ds cap, okay, or ds bar, and this is the electric field vector, so those are perpendicular to each other. Now there is no electric field due to third components. So pi 1 is equals to what about the electric field due to the inner part? So inside the conductor the electric field is 0. This is inside, this is just outside. So this inside the conductor electric field is 0, therefore there is no contribution to by the bottom area. So this is electric field due to outside is what? Simply E into A. Okay, so according to E into A, according to Gauss law, electric flux is equals to what? Electric flux through a closed surface is equals to 1 by epsilon times the charge enclosed. So here equals to E into A equals to, we don't know the charge, Q by epsilon naught, so we can write it as charge is equals to sigma into A, because it is a surface charge density. So surface charge distribution, charge is distributed over the surface, therefore surface charge density can be written as sigma is equals to charge per unit area, will gives us the surface charge density. From this expression I wrote Q as sigma into A by epsilon naught, so A got cancelled, therefore electric field at the surface of a charge conductor will be is equals to sigma by epsilon naught, and it is perpendicular to the surface, where n cap is a unit vector perpendicular to the surface. So what will be the electric field at the surface of the charge conductor? It is sigma by epsilon naught into n cap. Okay, so only this, only one first area, this first area only contribute to the electric field. Electric field due to second and third will be 0, and that is equals to sigma by epsilon naught. And the last property is electrostatic shielding. Let us consider a conductor. So, and this is a conductor of this thickness, and charge given to the conductor. Okay, if you give a charge to the conductor, or when the conductor is placed in electric field, okay, or when, first I want to discuss when what happens when charge given to the conductor. When charge given to the conductor just resides only on the surface of the conductor. Okay, and what about the electric field inside the conductor? Electric field inside the conductor is 0. Let us, I am taking one cavity, nothing but one empty space inside the conductor. I am taking one empty space inside the conductor. This is the conductor material, conducting material, and this is empty space. Okay, okay, according to this property, the cavity inside a charge conductor is electrostatically shielded or protected. Means electric field inside the cavity is 0. Whatever the charge you give it to the conductor, it doesn't affect the space inside the conductor, that is called cavity. So the best example is when during the thunderstorm, so it is wise to remain in the car. Okay, so there is a lightning here, lightning or thunderstorm. During thunderstorm there is a lightning happening here. During lightning you have to it is advised to sit inside the car, so that you will be electrostatically shielded or protected from the lightning. Why? Because a car, the material of the car is uh, conductor. This is a conductor. So whatever the electric field outside, okay, what amount of electric field may exist outside, okay, So the electric field inside the conductor will be 0. Electric field inside the conductor will be 0. That is why during lightning, so it is wise to remain in your car so that you will be electrostatically protected. Okay, this is about the electrostatics of conductors. Okay, thank you. The next topic is dielectrics and polarization. Dielectrics are non-conducting substances like insulators. They have no free charge carriers, whereas conductors has free charge carriers. Electrons are free charge carriers. So but the electrics have no free charge carriers. So in this class we will discuss how dielectrics and conductor behave when they are placed in an external electric field. Look at this figure. When a conductor which contain number of free electrons, when placed in external electric field, what happens? The free electrons displace or drift against the electric field. In the previous class I told that the positive charge move or drift in the direction of electric field and negative charges drift against the electric field. Here also, when a conductor is placed in external electric field, the free charges which are loosely attached to the nucleus, in the conductors, the valency electrons, the outer electrons are loosely attached to, so those become free at lower temperatures only. No, at room temperature only we have number of free electrons in the conductors. When we apply the electric field, they drift towards towards left of this conductor. If you apply electric field like this is the direction of the external electric field, E0, and when you apply this electric field, the negative charges in the conductor drift against the direction of the electric field and positive charges drift towards the electric field. So gradually one by one, so negative charge appear on this left side and positive charge appear on the right side. This will happen until the internal electric field or induced electric field is equals to the external electric field. Okay, so at a particular situation, so the net electric field, the outside electric field, this will continues, means displacement of charges continues till the electric field, net electric field inside the conductor is 0. Okay, so this is what happens when conductor is placed in a electric field. So already we have discussed in electrostatics of conductors. So when an conductor is placed in external electric field inside the conductor is 0, and this is the reason why, because induced charges are induced here. Actually there are no charges in the absence of electric field, but when electric field is applied, here charges are induced. So this is called induced electric field, which is towards left, and outside electric field it is towards right. So the net electric field will be 0. Why? Because both are in same magnitude and opposite direction, they will cancel each other. So therefore the net electric field inside a conductor is 0. Now we'll discuss what happens when a dielectric is placed in a external electric field. Now this is a dielectric material, any dielectric material. Air, examples of dielectric material, air. Okay, so air is a dielectric material, and see here, this is an example. So here dielectric is placed in external field. Here also negative charges slightly displaced towards the left side of this conductor, and we will see positive charge on the right side of the conductor. But this induced electric field, the electric field which is induced inside the conductor is having less magnitude compared to the outside electric field. See the arrow marks, this is a bigger arrow, so large electric field, but a very small or finite electric field is developed due to the induced charges. Okay, but the netted electric field inside a dielectric is not 0. So electric field here totally cancelled inside the conductor. Here in dielectric, electric field not completely cancelled. Some electric field exists. Okay, so inside the dielectric also, but inside the conductor net electric field is always 0, but inside electrics there exists some electric field. Now we will see, we'll study this same concept, dielectrics in molecular level. Okay, so here dielectrics are two types: polar dielectrics and non-polar dielectrics. First we have to know what are polar molecules and non-polar molecules. Okay, so first one is polar molecules. Okay, so if the centers of positive and negative charge coincide, positive charge and negative charge, the centers of positive and negative charge coincide at the same point, so they are known as non-polar molecule. First we are discussing non-polar molecules. The center of positive charge and center of negative charge lies at the same position, then that molecule is known as non-polar molecules. And examples of non-polar molecule H2 and CO2. Here this is a hydrogen atom. Okay, and the center of positive charge, right, center of these two charges, center of positive charge for a single atom, center of positive charge, center of negative charge coincide at the same position. Okay, now look at this carbon dioxide, center of positive charge CO2, the centers of oxygen, and centers of oxygen lies at the carbon, and center of carbon also lies at the oxygen. So here in polar molecules, what happens in a polar molecules? Polar molecules, the centers of positive and negative charges are separated by a small finite distance. These molecules have some permanent dipole moments. Okay, so these polar molecules are said to have some dipole moments. So here HCl molecule, H plus Cl minus, it is a positively charged ion, this is a negative ion, so they form HCl molecule. This is the center of positive charge and center of negative charge, and there is a separation between the positive and negative centers. So this is said to have some dipole moment. What is the direction of dipole moment? Represented from negative to positive charge. This is the direction of the dipole moment. And here H plus O minus, here the dipole moment is like this. Here the net dipole moment is towards like this. Okay. Just remember what are polar and non-polar molecule. Polar molecule, the centers of positive and negative charges are separated by small distance. Examples are HCl and H2O. Okay, whereas non-polar molecule, the centers of positive and negative charges coincide at a single point. Okay, so the net dipole moment is dipole moment P is equals to dipole moment P is equals to 0. Polar and non-polar dielectrics in external field. So this is a polar. Now we'll discuss how this polar dielectrics and non-polar dielectrics when placed in external electric field. Okay, so this is a example of non-polar dielectrics which has non-polar molecules. So in the absence of electric field, when there is no electric field, the centers of positive and negative charges at the same point, the dipole moment of this non-polar dielectrics in the absence of electric field is 0. But when the same non-polar dielectric when placed in external electric field is not 0, some electric field is there, external electric field, this negative charge is slightly displaced from the center of positive charge. So there exists small dipole moments. There is a dipole moment negative represented from negative to positive charge. So they have these molecules are said to be polarized. Okay, this is what happens when non-polar dielectrics are non-polar molecules placed in external electric field. So they don't their centers slightly displaced from their positions. Okay, so small dipole moment is developed. No, in the presence of electric field they have permanent dipole moment, but in the absence of electric field the dipole moment is zero. So this is what happens in non-polar dielectrics. So now let us see another example here. Polar dielectrics are the dielectric which contain polar molecule, that is a polar dielectrics. Now when polar dielectrics placed next to an electric field, what are polar dielectrics which contain polar molecule? What are polar molecules? In a polar molecules, positive and negative sensors are separated by small finite distance. So here, and the direction of this a polar molecule represented from dipole moment represented from negative positive charge. This is a dipole moment of this one, and this is a dipole moment of this one, and this is this and this one, and negative to positive, negative to positive, negative to positive. Okay, here these two will cancel like this, these two will cancel. So the net electric field, so these even though it has a polar dielectric have a net the individual dipole moments, but a net dipole moment is zero. The net dipole moment of all molecule will become zero in the absence of electric field. But when they are placed in external electric field, all the dipole moments come and align in the direction of the external field. So negative, 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 negative. Here negative charges will appear on the left, will move towards will move against electric field, and positive charge will move towards electric field. So in every molecule, you look at this picture. So in every molecule, negative charge is towards left, and positive charge is towards right. Now these are said to have some dipole moments. Net dipole, there is a net dipole moment. Okay, so this is about the polar and non-polar dielectrics in external electric field. In the absence of electric field, non-polar molecules don't have any dipole moment, but in the presence of electric field they are slightly polarized. And here, even though polar dielectrics have permanent dipole moments, but the net dipole moment in the absence of electric field is zero. But when the polar dielectric is placed in external electric field, there will be net dipole moment. Okay, so know these two. What happens to dielectric materials when placed in electric field? When dielectrics placed in an external field, they will polarized. Okay, so this is called polarization. The polarization is directly proportional to the electric field. Polarization is nothing but is dipole moment per unit volume. Capital P is equals to small p by V, number of dipoles which are aligned in the direction of the electric field per unit volume. How many number of molecules are aligned in the direction of electric field? Okay, that depends upon the strength of the electric field. So larger the strength, more and more molecules align in the direction of the electric field, and polarization will be maximum. So we can write it as P is equals to psi E into E. This psi is called electric susceptibility. Okay, So this is what dielectrics. Okay, so dielectrics are non-conducting. Dielectrics are non-conducting substances, like they have no free charge carriers. Okay, and how they behave. So when they are placed in external electric field, they are developed inside some induced electric field, but which in the case of conductors, the induced electric field is in equal magnitude that of the outside electric field. Therefore the net electric field will be 0. But in this case, the induced electric field somewhat less than the external electric field, therefore the net electric field will not be 0. So why it is like that? So we'll try to explain in this figure. So see here, so what happens when a dielectric material is placed in external electric field? They have dipole moments. Okay, so here this is a one molecule, so all the molecule towards near the right edge of this conductor will align like this in the presence of electric field. So there is a negative charge slightly displaces against the electric field, positive charge try to move in the direction of electric field. That is why these molecules, the molecules near the right edge will align like this. Okay, and the next molecules will align like this. Okay, and next molecule align like this, next molecule, and towards the left edge molecules align like this. So but when you see this arrangement, so this positive and negative charge near to each other close, the net charge will be 0 here. Here also the net charge will be 0, and here also net charge will be 0. Okay, therefore we have only charges on the edges. Okay, that is why so we will see only the induced electric field only due to these charges at the edges. So remaining charges are cancelled. That is why induced electric field is less than the outside electric field. That is why net electric field is equals to E induced minus E outside minus E induced will never be equals to 0. This is the reason why the net electric field exists inside a dielectrics, whereas net electric field inside a conductor is 0. Okay, thank you.